So today we're going to be talking about percent composition and how to do the math problems with this. So if you look at a compound like this, think no different than if you were looking at the parking lot. And I asked you what's the percentage of red cars out there? What's the percentage of white cars out there? Or anything like that. What would you do? You would take a part that you're talking about and that you would divide it by the whole. And then you'd either move the decimal point over two more, or else you would go and times it by 100. And that's how we find the percents of everything. So this right here is the same exact way. And we'll need to have our calculators also. Let me pause. So we do this percent by mass. So let's look at strontium. Okay, and then we'll look at chlorine. And there's two of those, so we need to take that into effect, counting too. So let's go ahead and look up strontium and look up its mass. And it is 87.62. Okay, and then we've got to take chlorine times 2. Okay, and so let's figure out those values. This one here is pretty easy. It's 87.62. And then let's calculate this one. Okay, so here are both of the parts. Here's how much strontium has a mass of, and this is the mass of chlorine. So now we need to figure out, so that's each part we can figure out for each one, but we need to figure out our whole. So we'll add these two up. So, okay. What'd you guys get? Anybody? Okay, so now we're going to take each one of these parts. We figured out what the total is right here. That's what this is. And we're going to take each part and we're going to divide it by the whole. So here is the 158.526 divided by 158.526. Okay, and then don't forget to multiply it by 100 or else move the decimal over twice. And so let's figure out those two values. So when you get into your calculator, don't forget you got to times it by 100 to get your percent. And then look at this. Our percents are going to add up to a perfect 100 right here. So that's a way that you can double check it. I mean, I know that some people will go and figure out one and then they'll subtract it from 100 and figure out the other. But really this is like a way of accounting where you're figuring it out and then double checking with the 100%, making sure that it adds up. This right here is actually 99.99%. Sorry about that. But anyway, you can double check it with your percentages and adding them up. Let's look at this one. It's a big one. Okay, so we'll look up our carbon. We've got to take 12.0107 times 6. Got to take our hydrogens, which is going to be 1.00794 times 12. This is sugar, by the way, glucose. And then oxygen, we're going to take it 15.9994, and we're going to take that one times 6. So let's pause it here, and then we'll figure out how much each one of these equal. 88. Perfect. Okay, so we went and we figured out each one of these by multiplying by 6, hydrogen times 12, and the oxygen times 6. And so then we went and added up those to figure out our total. Because remember, it's a part divided by a total. So you divide by 180.15588. Divide by 180.15588. Because again, part divide by whole, part divide by whole, part divide, and each one of these parts, when we figure out a percent, should be up to 100% or else really super close to it. So we're going to go and divide all these and figure out our percentages. Don't forget to take each one of these decimal values and times it by 100 to get your percents. And we don't have any kind of significant figures on these, so just bring them out to hundredths for me. Okay. I'm going to pause it while we figure out the percentages. You do the same thing. Okay, so this turned out great. We went and divided them and multiplied by 100, and we got each one of our percents. They do add up to 100%, so that really shows our accuracy. So Okay, so we're going to move on now to another type of problem. Okay, to a second type of problem. Not yet. We're doing another percent composition, but this is different. They are giving you values of each one, so that's pretty nifty. So what you do for each one of these, here we've got potassium, and it is 1.04. So we've got our values already figured out for us to figure out our percents. So we're going to have to add these up to figure out our total. We've got chromium right here, and it is 0.70 grams. And then we've got oxygen right here, and it is 0.86 grams. So we've got each one of our parts right there. So now we can figure out what our total is, and then we can divide each one of these by the total to get our percents of each one. So it's kind of like we're skipping a step on this one. And also our answer is going to be in 2 sig figs, so that's going to make it a little bit boring, but we'll get there. Okay, so we took each one of these values in here and divided by the total of 2.6. Okay, and so now we're going to figure out the percents of each one. Don't forget to multiply by 100 or else move that decimal over twice to get your percents. And so go ahead and take a moment and pause, and we will figure out the answers to this. Okay, so we can only have 2 sig figs in this one, so we rounded each one. This right here could have went on as many sig figs as you need, but we rounded the rest of them. So we got 27% for chromium, 33% for oxygen, and then you add them all up and you get a perfect 100%. That's great. So this right here is a little bit shorter than the previous type of problems like this, because you had to figure out what your values were for each one and multiply each one. Well, that was already done for you. They have this sample and they figured out the grams, so they had the parts all figured out for you. So you just needed to calculate it and divide by the wholes. Okay, empirical formulas is very different. Now, when we go look up something like hydrogen peroxide like this one, this is the molecular formula. And if we were going to find the molar mass of it, we'd have to take 2 hydrogens and 2 oxygens and we'd have to add it up. Okay, but the empirical formula is actually simplifying each one of these ratios. There's a 2-to-2 ratio, which is the same as a 1-to-1 ratio. So the empirical formulas are much more simplified. And then like right here's our sugar, our glucose, and this right here's got a 6-to-12-to-6 ratio. So a 1-to-2-to-1 ratio is what we're going to be looking for. So now we're going to figure out a way to go and calculate this and figure out these empirical formulas. So it's pretty nice. And so what we need to do is we need to figure out the masses of each, so they're provided for us. Okay, and oops, this needs a grams there. Okay, and then you need to determine the moles. To determine the moles, we're not dividing by the whole like we did for percent composition. We're dividing by the atomic mass of each one. So let's go ahead and get started on this one. We're going to take calcium, Ca, and we're going to take its mass on here, and it is 13.5 grams, and we're going to divide it by calcium's mass on the periodic table, which is 40.078. Okay, and that's going to give us the number of moles, and that's what we want, because really, I got to show you something really quick before we go on further. This is 1 mole to 1 mole also, this ratio. This is 1 mole to 2 moles to 1 mole. So we're going to figure out the moles so we can put that number here and figure out what the formula is. That's what the whole idea is of this one. So go ahead and continue with me with notes. Oxygen, we've got 10.8 grams, and we're going to divide by, oh, I should have put grams there. Anyway, so remember these are grams per mole, so that's how we get a mole out of it. And then 10.8 divided by the 15.9994 grams. Okay, and then let me expand my page here. Okay, then we've got hydrogen, which is 0.675. They're trying to keep these all 3 sig figs. Okay, and we're going to divide by hydrogen's mass, 1.00794 grams. Okay, so let's take a minute and do that. We don't need to come up with the total of this. We just need to come up with the moles by dividing these. If we get some funky numbers, then I'll teach us how to deal with it. Okay, so go ahead and pause it and figure this out. Okay, so we divided each one by their mass on the periodic table. Okay, and then we get these ratios, right, these numbers for each one. We don't have times by 100 or anything like that, but just look at this. I don't know if you can see this, but this is a 1-to-2-to-2 ratio. So just think about this. How could I figure this out if these numbers look too strange for me to figure it out? Well, divide by the smallest one. So if I take it and I divide each one of these by the 0.336, and I don't think you need to go out by so many decimals, but it's just my practice. Okay, oops, wait a minute. I just screwed up here. Let me fix that. 0.336 we'll divide it by. Divide by 0.336. In fact, 2 decimals would have been really pretty right here. It turned out pretty nice. Okay, and you should get something really close. So, can you figure out the top one for me? And then, can you figure out the second one for me? And then the third one. And what do you get for a value when you do that? So if you couldn't see these values here, you could always divide by the smallest to see it. What'd you get? 1.99. Oh, I was going to say, that's not working right. Okay, what do we get for the next one? 2.01. What do we get for the top one? Well, that's a 1. What am I thinking? Okay, so look at this. This is a 1 to 2 to 2 ratio. So that is telling us that we've got 1 calcium, so Ca is 1. We've got 2 oxygens, and we've got 2 hydrogens. You know, if you think about it, our formulas, this one here does not, this starts with a metal. So it's not like it's going to be like sugar where it has all of them separated like this. Since it starts with metal, this right here is probably a polyatomic ion. And we do have one. It's CaOH, it would be hydroxide, and 2. So going from this step to this step is a great understanding of what you're doing. I expect to see this one right here for sure, but it's really great when you can do this one. Okay? So let's try another one. One more, and then we're done for today. Okay, so what we need to do, we've got a sample of copper metal is weighing 2.5 grams and is heated to form an oxide of copper. The final mass of the oxide is this much. Determine okay, so what we've got is we've got copper weighing this much, 2.5. Okay, and then this is kind of fancy how they wrote this in the problem, because the oxide, the copper oxide, CuO, I don't know what it is. I don't know what these values are on this. Okay, anyway, we know that the total sample weighs 313. Oops, I should have wrote 313. So that means that the oxygen on this thing, we got to subtract the 2. Okay, so it's going to be 0.63. Okay, and so now we've got our 2 values here. We don't even need this one anymore. And so we'll go and divide them by each one of their atomic masses. If I remember right, copper is 63.546. Okay, and then oxygen, we remember, is 15.9994. Okay, and then so we can find our moles again. So let's take a moment and calculate that and figure out what our mole ratio is. And I'm sure you can see once you calculate this that you've got a 1-to-1 ratio. So it's going to be CuO. And that makes sense because copper, just a reminder here, copper could be a +1 or it could be a +2. And oxygen is definitely a -2. So it was actually a copper 2 oxide is what this one is. So it's just CuO. Okay, I like going through and double checking with my ions and doing my switcheroo or whatever I need to, if I can, to double check my work. So that's how we found the empirical formula, and that's where we stop today.